So Edward Lee is the Robert S. Pepper Distinguished Professor Emeritus and Professor of the Graduate School in Electrical Engineering and Computer Sciences at UC Berkeley. So his research has pioneered model-based design, which is what this talk is, what I hope is going to teach you, model-based design for embedded and cyber physical systems, including the Ptolemy project, emphasizing deterministic models, time, and concurrency as foundations for reliable engineered systems. He directed Berkeley's Industrial Cyber Physical Systems Research Center, previously chaired the EE division and the EECS departments, and authored this book, which I hope he's going to tell us about today, called Plato and the Nerd, which, quite frankly, I think is one of the best, most interesting books I have read in a very long time, and I recommend it to my entire team to read it. So this,
I have it here.
there you go. It's and it's available free online. So this book examines how engineers create with abstractions and how technology and culture shape one another. So on that note, Edward, if you'd like to add any additional information about your introduction, please go ahead.
Okay. No, this sounds good. I think I'll maybe go right into it, I think this is really going to be pretty different from the usual meeting, but hopefully this will be kind of fun and a bit more philosophical, and I would welcome discussion while we go, right? So it's been a while since I've given a talk about this book because the book was published in 2017. I've been every 2 or 3 years teaching a freshman seminar out of it, which has been kind of fun. And each time it sort of surprises me that the book doesn't seem to have gotten stale in that time. And hopefully you'll have the same reaction. But, it really is kind of a philosophical view of our field. And I think it is relevant to the work that this group is doing on the Ethernet. But I want to tell you a little bit about why I wrote this book, because it started kind of in a fit of anger at my colleagues. I had relatively recently, stepped down as chair of our department, which is a unified EE and CS department and where one of the real strengths, I think, in the department has been a lot of interaction between, people who are more traditional electrical engineers and people who are computer scientists. And there was a faculty meeting that occurred in 2016 where it was suddenly revealed to us that a bunch of the computer science faculty the senior computer science faculty had organized a coup attempt and wanted to essentially create a school of computing separate from the College of Engineering. And they wanted to pull out of the College of Engineering. And there were a lot of discussions that happened around that time. And one of the things that I realized in the course of those discussions is that none of us, myself included, really had a good solid sense of what engineering is. And so I happened to have a sabbatical that was starting around then. And so I kind of dropped all the technical stuff I was working on and started reading a whole bunch of things and started working on this book, and basically wrote it over the course of about 9 months. And I learned a lot in the process of doing the research. So just to, tell you a little bit about the title, right? What does Plato and the Nerd come from? Well, it was partly inspired by this fresco called School of Athens, which is by Raphael, and it's in the Vatican. If you've visited the Vatican, you probably saw it. It's part of I've zoomed in on a particular part of this fresco, which shows Plato and Aristotle in the center of the fresco. And Plato is kind of pointing up to the heavens, and Aristotle is sort of waving at the ground. And it's suggestive of a really contrasting philosophy between these two, um, you know, Greek philosophers, where Plato emphasized kind of the Platonic ideals, that to him the real reality was the abstractions of, you know, an idealized world, whereas Aristotle was more about kind of discovering the world empirically, and that the properties of the world reveal themselves from the observations of the actual physical reality. So these are sort of contrasting and really very complementary perspectives. And to some degree, I kind of, in the process of writing this book, had a kind of epiphany about the work that I had been doing for the last 30 years at that time. So, you know, the cover image has this um, sort of Escher-like feedback. I originally tried to do this based on the original Escher drawing, and then approached the Escher Foundation for copyright usage, and they first said, well, they were going to charge me an enormous amount of money to use the actual Escher drawing, but worse, they wouldn't allow me to modify it. So I couldn't make one of the hands a robot hand. And so I decided to make my own drawing inspired by the Escher drawing. And this is actually a photograph of my own hand. So that was kind of a fun project. But anyway, these are, you know, machines and humans kind of designing each other. And this became a major theme of the book. So maybe I can go through, you know, a bunch of the sort of perhaps somewhat challenging ideas that this book addresses, right? One of them is this idea that technology advances as a consequence of scientific discovery, right? I mean, I think that's a pretty widely held view, and I really challenge that view in this book. And so, you know, one of the things that that I address is the relationship between discovery and invention. Okay, so these three guys got the Nobel Prize in 1956 for discovering the transistor effect, was the way the citation read. Now, the Nobel Prize, it is not given for invention. That's specified in Alfred Nobel's will, okay, that it's not given for invention, it's given for discovery. And so the transistor was not invented by definition by the Nobel Committee. It was in fact discovered, and it was the transistor effect that was discovered. Now, never mind that the transistor effect has never been found anywhere in nature. So that's an interesting discovery, but nevertheless. But it turns out that actually the transistor had been patented in 1930. So there's a patent issued to Julius Lilienfeld that describes actually a field effect transistor. So, you know, the three guys actually had designed a bipolar transistor, which is, you know, a bit different physics, but the field effect transistor is actually the one that's in most widespread usage these days, except niche applications that are high power applications, right? So this is the basis behind CMOS, and this was actually patented in the 1930s, in 1930 actually, well before the Nobel Prize. So, but of course this was an invention, not a discovery, and that was obvious because it was a patent, right? And so it wasn't eligible for the Nobel Prize. But this line of questioning led me to this epiphany that I was almost embarrassed when I realized what was going on here, because it sort of framed the work that I had been doing for my entire career in a way that explained it a lot better than I had ever been able to explain it before. And so, one of the things, for example, is Paul mentioned that I have been kind of obsessed with deterministic models for my entire career. And I've always struggled to defend those, right? Because, people come to me and say, well, why on earth would you be talking about network distributed systems with deterministic models? I mean, the fact is, in reality, shit happens, right? And stuff goes wrong. And, so deterministic models are going to be unrealistic. Um, so why bother with them, right? Well, so this is the framework that really explains that, right? So it has to do with what is the value of a model. So in science, the value of a model lies in how well its behavior matches that of a physical system. That's what scientists do is construct models that are supposed to reflect the physical reality. In engineering, we do the reverse. The value of a physical system lies in how well its behavior matches that of a model. If you're going to create a piece of silicon, you want that piece of silicon to match the synchronous digital logic model that you've specified. And the silicon is worthless if it doesn't match, right? It's not the model that's worthless, it's the silicon that's worthless. And that's a mirror image of the scientific use of modeling. So one of the things that I realized in this process is that often when people talk about models of systems, they don't know whether they're talking about scientific models or engineering models. So I do a lot of work, for example, in real-time systems, right, where you try to get processors to behave in a timely way with respect to some physical clock. And the reality is that most of the real-time systems community primarily uses scientific modeling instead of engineering modeling. They don't specify timing behavior and then try to make the system conform with the timing behavior. Instead, what they do is they implement software, map it onto a microprocessor, and then try to figure out what the timing behavior is. Okay. And to me, this has always impressed me as backwards, that we would really be much better off if we actually specify the timing behavior and then make the physical system behave that way. So, a few other ways to think about it is, a scientist asks, can I make a model for this thing? An engineer asks, can I make a thing for this model? An interesting corollary of this is that a scientist tries to shrink the number of relevant models, whereas an engineer tries to grow the number of relevant models, right? The more models we can make physical things match, the richer our ability to create interesting systems becomes. So, so this really sort of turns on its head this question about, technology advancing as a consequence of scientific discovery, because it suggests that, well, the synthetic process of engineering is actually very complementary, where engineers can create things that never existed before, whereas, discovery is fundamentally about finding out about things that already exist. So the second issue is this idea that engineering and science are rational, systematic, and logical. And I challenge that in this book. So one of the things that I talk about in the book is, the famous Donald Rumsfeld's classification of, you've got your known knowns, you've got your known unknowns, and you have your unknown unknowns, right? But this looks really incomplete to me, because there's obviously a fourth category, right? The unknown knowns. And the unknown knowns, to me, are the things you know, but you don't know you know them. Okay? And we all have them. These are our biases. These are our ways of thinking that are shaping our judgment, shaping our choices, and we're unaware that they're there. Okay, so Thomas Kuhn, the famous Berkeley philosopher, of course, laid this out in his book called The Structure of Scientific Revolution. And he made it really very clear in this book, which was really extremely controversial at the time, but he used the term paradigm and really established our common current usage of the term paradigm, where a paradigm is a framework of thinking um, that often forms an unknown known. The paradigm is the backdrop against which you're making all your decisions and judgments that you're largely unaware of because it's just your way of thinking. And Thomas Kuhn claimed that the major scientific revolutions come when paradigms are replaced with new paradigms. So um, examples of paradigms that we work with in the context of engineering are the various levels of modeling that we do, right? So I have a chapter in the book that's entitled Models of Models of Models of Things. Okay, so at the lowest level, you've got things. This is a FinFET transistor. This is from this particular gate, this particular piece of silicon was made one floor down from me here. I'm on the 5th floor of Corey Hall right now. It was made in our microlab on the 4th floor of Corey Hall in 2001. And it was the first really three-dimensional transistor design that became then, the mainstream design for transistors. But this is a very, a very physical thing, but it has its own abstractions, right? I mean, the concept of design rules that are used to, construct silicon chips gives you kind of a paradigm within which you can work. And it's a paradigm that is very effective because, the manufacturing technologies are such that they're able to give you useful circuits as long as you conform with each of these design rules. Whoops, I'm going the wrong direction. So, given these design rules, you can design chips is effectively designing masks that conform with the design rules. And then you can go one level up from that to circuit diagram where you're talking about, transistor abstractions. And then, you go one level up from that and you have gates. And now you can talk about wiring together gates and, you no longer, you can forget about the three-dimensional structure of the transistors at this point and just worry about, where do you put your latches? How many gates are between latches? So then you can go one level up from that and, design an ALU, and then the ALU becomes a component in a register transfer level description of a microprocessor. Um, each of these layers is fundamentally a Kuhn style paradigm within which you can do design, right? And anyone who's working at any one of these layers um, thinks of the layer below as the implementation, right? So the implementation of this microprocessor is this network of gates, and the implementation of this network of gates is the gates themselves, and then the transistors that form the gates, and then the mask, and then ultimately the piece of silicon, right? So these are each implementations. So the distance between these is pretty huge, right? So we can put billions of transistors on a die. And I like the observation that this only takes the paradigms through the hardware to the level of the chip, but then go above that to instruction set architectures, and then programming languages, and then libraries, languages, and dialects, and up to cloud computing abstractions. And the dynamic range of all of this is really extraordinary. So there's a really nice quote from Dijkstra way back in 1972, where he said, "I don't know of any other technology covering a ratio of 10 to the 10 or more. The computer, by virtue of its fantastic speed, seems to be the first to provide us with an environment where highly hierarchical artifacts are both possible and necessary." So the 10 to the 10 here is the difference between the stuff going on in the silicon and the stuff going on in the program. Okay. So I did a back of the envelope calculation of where we are on this today. And well, at the time of the publication of this book, it was more like 10 to the 24. Okay, the difference between what's going on in the silicon and what's going on in the high level programs. So extraordinary dynamic range involved. So one of the things then that I develop in this book is this idea that, well, if each of these layers is a paradigm, right? And paradigms are, according to Thomas Kuhn's philosophy, they're not just objective truths about the world. You might like to think of them that way, but they're really much more cultural artifacts. And so I developed this idea in that the the world of computer science is actually full of subcultures, and these are very much cultures in a very human sense, right? You have um, you know programming languages like COBOL at one extreme versus APL at the other extreme. When I was studying computer science at Yale way back in the 70s, we had a room full of terminals that had the keyboard keys replaced with APL keys. So there was a key that had this triangle with a vertical slash in it, and there was a key with a leftward going arrow. If you wanted to actually type a letter to someone, it was rather difficult to do in this particular room full of terminals because you had to somehow map all these strange looking keys to letters, but that wasn't the intent. The intent was to write APL programs, and so APL was a bit of a fad for a while within a subculture in computing, and you certainly see these fads today, right? I mean, people who love functional languages exist in a world of their own, and are just horrified at the banality of an imperative program, right? And that's it's a culture. It's very much a culture, and it's quirky and it's idiosyncratic, and yet it shapes our thinking, right? When you work with a programming language, right, you might think you're objectively constructing some objective artifact, but no, you're expressing something within a culture, within a cultural tradition, okay, very much influenced by your predecessor humans who affected the tools and the languages. Okay, so this calls into question the notion of engineering and science being rational, systematic, and logical, and puts them sort of more squarely in a cultural perspective. The third misconception that I address in this book is that technology is top-down intelligent design made by humans. That I don't really buy anymore. And in this book, I kind of present technology development as being actually just a symbiotic coevolution, that humans, in a cultural sense, in a mimetic sense, right, um, uh, are co-evolving with the technology. Um, and here's a direct quote from the book, right? Are we playing God, creating a new life form in our own image, or are we being played by a Darwinian evolution of a symbiotic new species? Are humans the purveyors of the noisy channel of mutation, facilitating sex between software beings by recombining and mutating programs into new ones? Right? I mean, who writes a program from scratch? Nobody. Well, maybe the introductory programming class that you take in a community college might try to get you to do that. Now, of course, it's a ridiculous thing to even attempt to do because the students are all going to ask ChatGPT to write the program. But um, but you know even without the use of AIs, right? Programming is more about assembling the work of others than it is about creating something from scratch. And so the work of others, the libraries that you use, the mechanisms by which you use the libraries, the patterns, the idioms, these are all, part of a coevolutionary process. the tools that influence the way that you build programs. I mean, these days the AIs are, tremendous boon. They tremendously improve my own productivity. But this idea then developed into a whole nother book that got published in 2020 called The Coevolution, which is also available open access. And this one very much zeroes in on this idea of symbiotic coevolution between technology and humans. A fourth misconception that I address is this question, this assumption that computers are universal information processing machines. I'm actually working on another book now that is trying to counter this perspective that has become disturbingly widespread, that is sometimes called pan-computationalism, which is that actually everything in the physical world is a computation. And, there's sort of extreme forms of this that include the idea that we're actually living in a simulation in some sense. So this pan-computationalism, I think, is profoundly wrong. And there's, a lot of reasons for this, but in Plato and the Nerd, I lay out, the beginnings of the argument against this, right? And so it talks a bit about, what is information processing, what is, the people get confused by the use of the term universal in universal Turing machine, right? In what sense is a universal Turing machine universal? Well, it's universal in the sense that it can realize all Turing machines. Many people mistake that and say, no, it's universal because it can realize all machines. And that's simply an indefensible position. And I lay out a whole series of arguments in this book about why it's an indefensible position. I also point out in this book, however, that this very idea of pan-computationalism is actually not falsifiable by experiment, that it's actually impossible to construct an experiment that will prove that thesis false. And one of the root reasons for that is the results in information theory by Claude Shannon. Okay, and so I'm not going to go into the detailed argument here. You'd have to read, if you read chapters 7 through 9 of Plato and the Nerd, you'll get that story laid out from the ground. There's a sort of very gentle introduction to information theory. What was Claude Shannon's basic result? And then how does this apply to this idea of computation being at the root of everything? And it leads you to the conclusion that it's actually impossible to construct experiments that would falsify this thesis. And then points out that according to the philosophy of science that was popularized by Karl Popper way back in the 60s and 70s, any thesis that is not falsifiable by experiment is not a scientific thesis. It's a faith. And it can only be taken on faith. And then I lay out arguments about how, well, you could just take it on faith and run with it, but it turns out you can show that it's actually an extremely inconvenient thesis, that it results in throwing out most of the best theories that we have in physics, for example. And so inconvenient theses that can only be taken on faith should be rejected. So part of this argument is addressing this question of whether the physical world is actually a digital algorithmic process at its root. And this idea has been pushed by a number of very smart people, including John Archibald Wheeler, who coined the expression "it from bit." And but Wheeler himself argued that there were some limitations to this. So he pointed out, for example, that nobody at that time had ever figured out how to quantize time. that physics didn't yield to quantizing time. And people are still trying to do that, to show that time is fundamentally quantum, and so far have failed. And my argument in this book is that they will continue to fail because it's actually an unfalsifiable thesis. And consequently, it can only be taken on faith. So one of the issues that I address then is the question, well, there's various people who buy into this pan-computational thesis and take as a corollary that our cognitive minds must be computations. And if our cognitive minds are computations, then we should be able to become immortal by one mechanism or another, right? Essentially an uploading argument. And I think that that thesis is, resembles a medieval faith. And that's kind of the story that I lay out in this book, and point out that if in fact cognition is not a digital algorithmic process, then it may well be that your mind is actually entirely your own and you will never be able to do any uploading. So this question of, an untestable thesis leads inevitably to, another sort of problematic assumption that ultimately anything can be understood and explained. And it calls into question that, right? Particularly if we buy into, an empirical, sound scientific method, then, if you have theses that matter a lot, they have profound implications, such as whether or not we could become immortal, and they're untestable by experiment, then, the scientific method falls short. We're going to be unable to use it to answer those questions. I also give kind of a tutorial on the incompleteness results of Turing and Gödel, which apply really only to computational systems. And so there's further incompleteness in the physical world that doesn't even require assuming a computational paradigm. And one of the issues that I address in this book is determinism in the physical world. I can show mathematically that it is actually incomplete. So if you take any set of deterministic models that's rich enough to include Newton's laws are widely assumed to give a deterministic view of the physical world, and they actually don't. But if you take any set of physical models that is rich enough to include Newton's laws, that set is incomplete. It doesn't include its own limit points. And one of the consequences that immediately arise from that is that in such a set of models, non-determinism is inevitable. And in this case, non-determinism is not about a probabilistic issue, right? Probabilistic issues are epistemological. They're about what we know, not about some underlying reality. The non-determinism that I'm talking about here is about an underlying reality, and it gives kind of a mathematical argument that uncaused action is actually allowed by these physical theories, that you can have stuff that happens with no cause. That's the form of non-determinism that arises from this incompleteness. And interestingly enough, recent experiments in quantum physics around this idea of indefinite causality have shown experimentally that uncaused action is actually a physical reality in certain systems. So this, calls into question the determinism of the physical world that was nicely laid out by Pierre-Simon Laplace, who, postulated Laplace's demon that, was this demon who, if it knows the current state of the universe, can predict all of the future and know all of the past. And I go over some of the discussion that's happened around this. So, did quantum mechanics dash this hope? Well, Stephen Hawking said no. In fact, Stephen Hawking said that quantum mechanics just moves the goalposts. And he points out that Schrodinger's equation is a perfectly deterministic equation, and therefore, quantum mechanics can still be interpreted as a deterministic theory of the physical world. David Volpert, who some of you know, I think, very, very interesting guy working at Santa Fe Institute, gave a proof that Laplace's demon cannot exist in the physical world in which it's doing prediction. And this is kind of a Gödel-like incompleteness argument. And so Laplace's demon would have to exist outside the universe that it's predicting, which starts to sound now like a god, right? So yeah, so I also show that determinism is incomplete, as I mentioned. And so as a consequence, the physical world actually does intrinsically have some non-determinism in it. And then I also have a chapter in this book that says, well, does this mean we have to do probabilistic reasoning? And I point out that actually much of the theory of probability was actually developed by Pierre-Simon Laplace. A lot of the techniques that we use in probability today were developed by Laplace. And there's actually no contradiction there because Laplace was fundamentally a Bayesian. So to a Bayesian, the meaning of probability is it's a measure of what we don't know. It's an epistemological phenomenon. It's not an ontological phenomenon. It's not a measure of randomness in the world. It's a measure of what we don't know. And so I have a chapter here that kind of introduces what is this Bayesian line of reasoning. And one of the quotes from the book that I really like is anytime we talk about what we don't know, we can't know what we are talking about. So anyway, so I have a chapter on AIs and that, is dated, of course, at this point, although surprisingly durable in the comments that it makes. I mean, one of the things that it addresses is, the debate at the time about whether self-driving cars should be allowed on the road and, should we require them to have solved the trolley problem before we let them drive cars? Well, I point out in this book that by that line of reasoning, we shouldn't let humans drive cars because humans haven't solved the trolley problem either. So maybe we shouldn't let anyone drive cars. So anyway, so I also raised the question of, do we really want computers with human-like intelligence? And here's another quote from the book. I really do not want to have to argue with my car about getting to school on time. It's hard enough to have that argument with my daughter, right? So anyway, that's kind of a sort of thumbnail sketch of what's in the book. I originally thought that it would be suitable for general audience. It turns out it's not so easy. It's not such an easy read. It requires some technical background. I discovered this when I used it in these freshman seminars, which drew people from all fields, right? So, I mean, it was dominated by people who intended to major in computer science, but occasionally I would get people in from political science or cognitive science or some other field. And there were parts of the book that they found pretty difficult. One of the things that I think one consistent piece of feedback that I got from the students was that they really liked the introduction to information theory. The fact that I was able to give them a sense of, what it means to quantify information. And I think I'm proud of that chapter actually, because I think it really is pretty accessible for non-technical people, and it really fully develops the core results from Shannon. So anyway, so let's switch to discussion, and if you want to dive into any of these topics in a little more detail, I'm happy to do that.
So let's go around the room. Who would like to raise their hand if they have a question? Well, I don't see any raised hands, so let me kick it off. Oh, I see. Okay, there came quite a few quickly. All right. So I've got questions from Pankaj and Sahas. Pankaj, why don't you go first?
Sure. First, I want to thank Ed for a really thought-provoking talk. I think it's so profound that reacting to it feels like a shameful thing to do. So I apologize first for asking a question so promptly. I should be thinking a little bit more about what you just said, maybe for the next few weeks. Uh, but uh, but such is the nature of these seminars that we have to ask a question now. Um, I was reminded in your comments about uh, context, I might say, in AI. Um, the whole thing about unknown knowns that you said is really profound in terms of the systems we are building and how we are dancing around the idea of context and capturing context. Uh, in its simplest meaning, one could think of context as everything that has happened before. Um, and I find we haven't picked up on McCarthy's writings from 1995. This is his writings on context with Guha are some of the last things that he did as a scientist. And I think some of the things he said are really profound, like context is the missing facts and relationships that you could bring a situation to turn it into an axiomatizable world, for example, so we could reason with it. And I see, in chain of thought prompting and such things, that lack of thinking about context and the unknown knowns uh, is forcing us to build systems that feel like expert systems of the 1980s. And I'm afraid AI will fail from not paying attention to things like this. I would really love your comments on that, if you could add.
Yeah, I think that's a very good point that you raise, and there's a whole bunch of different rather subtle aspects to it. But one of them is that because of the way AIs are trained, on all of this archive of human creations, right? All the all the text and so on um, that they're trained on, they really potentially in a very strong way codify today's paradigms. Now they do have the advantage that because they are more widely read than any of us could ever possibly be, that they end up codifying a multiplicity of paradigms, and they can, for example, I mean, I do a lot of work with Cursor these days, which has a built-in AI for helping with coding, and it very comfortably moves between the worlds of functional and imperative programming, whereas I don't know many humans who do, right? They
Yeah,
just they fall in one camp or the other, and they're very uncomfortable in the other camp. And so in some ways, the fact that they are have in fact absorbed I would say a multiplicity of contexts, right, rather than just a single one, could be very helpful. This is also true, if we, sort of systematically work on trying to make their training data sets broader in a worldwide multicultural sense, right? Give them more exposure to lesser used languages and cultures with, less known, widely known traditions. Then, having these tools that can easily move between these different subcultures could actually help humans do the same thing. That's sort of an optimistic view. Um, yeah, so that's something that I think could be an outcome of this. I certainly see it in the coding world because I mean I was using Cursor to have it teach me Rust, and learning how to do the memory management in Rust is a little bit of a mind bend, right? There's a paradigm there, and the AI helps a lot, right? I mean, I could sit down with a tutorial, and 2 hours later I might have some insights, but On the other hand, I give it a little chunk of C code and say, how would you do this in Rust? And it gives me something and I say, oh, wow, that's cool. You know, and I learn something more quickly.
Yeah. Yeah, I think, if I may follow up just a little bit, I was reminded also of a book by Malcolm Gladwell, of all people. Um, I think it was Blink, where he said that the infosphere is actually shaping us. And if you think about it, uh, what happens in politics and social media, which is computer mediated these days, it really is true. And I think what you did today was, you focused on scientific and engineering work, and you showed how true it is. It might be there, and I really like your argument. So thank you for the talk, and I hope we get to talk to you again.
Okay, let's take a couple more people. Sahas, you are next, and then Hisham. Go ahead, Sahas.
Yeah, Edward, yeah, thank you for your book. I think Paul gave it to me right after I graduated, and I kind of slowly read it over next year and a half. But yeah, it was good. So yeah, a few things really stuck out to me. So in this, like, you talk about models that scientists make better models, engineers make better systems that apply to the models. And in this kind of like this pattern, like what makes a successful model, right? Like a Turing machine, it's not really a model any engineer works to. It was useful to prove some things 50 years ago, but it's still arguably a successful model. And then I guess the second part of my question is, as these models kind of uh, go on, like you talk about like the layers of models, where if your layer doesn't map properly to the reality of the layer underneath it, then it introduces non-determinism. So is the evolution of these models to kind of collapse these layers of additional non-determinism?
Yeah, excellent question. I have actually a slide that I'd like to show that. Let me go back to sharing, that I think makes a really audacious attempt to answer this question. This is gutsy, right? So the idea here is you've got models, you've got things. Okay, and so this is a Kantian view, right, where the things are the thing in itself, and the models are mental constructs, perceptions of these things, right? And as I was pointing out, in science, you try to make models that match things, and in engineering, you try to make things that match models, right? But we use a multiplicity of models, and we'll abstract models and we'll refine models. So if you think of, a C program as a model, or a program, or a Rust program, and you run it through a compiler and you get, another model in an instruction set architecture, and then you refine that further and map it onto a piece of silicon to get an execution that's an actual thing, right? So then, the question is, when are these models useful, right? That's, I think, the question that you were addressing. And
Yeah.
of course, it really becomes very important whether you're trying to do science or trying to do engineering, right? Because an engineering model is not going to be useful if you can't make things match it, right? And a scientific model is not going to be useful if it's not a good description of things that exist, right? So those are easy criteria. But once you start layering models, which we all do, in fact, most of us are working many layers up from this, all right? And so the connection with the physical things is so tenuous and so distant that it's hard to use that criterion to evaluate the quality of your models, right? And so there, I think, is where things get a lot harder. But one of the observations is that fundamentally, this relationship between models is a mathematical relationship. And so here in one audacious slide, you have engineering, science, and mathematics all kind of showing how they work together in our disciplines. But yes, I think your observation is very good. It's very difficult to evaluate how to, how do you decide when models are good and when they're not. And I think this is, partly where the cultural context starts to really weigh heavily. And I think often we let it weigh too heavily, right? We have too many unknown knowns. And when we're trying to evaluate the quality of a model, the value of a model, the unknown knowns are going to very much dominate our thinking. The background paradigms, the things that we're used to, our usual way of thinking is going to affect our assessment of the value of the model. And that's not ultimately going to be an objective judgment. It's going to be a subjective judgment.
So Edward, along those lines, standards today like IEEE 802.3 are written in words like should, shall, and may. And there's a wide variation in how those words and sentences can be written in those standards, and an even wider variation in how they can be read and interpreted. Now, this has led to the idea of interop conferences and plug fests to make sure that things actually work together, which is a very pragmatic engineering solution at the time. But what we've seen over the last 50 years is this results in the dominance of one or a small number of companies that you have to be compatible with in order to sell your product. So here's my question. Is it possible to design a standard as a mathematical model instead of a thing, where everyone has to be compatible with the model and not some arbitrary implementation that has, essential bugs, misinterpretations, and intentional or otherwise shortcuts in their design, manufacturing, and programming?
It is possible, and has been done. So the standards around video coding, MPEG and all of its successors are defined in a programming language that was developed here at Berkeley by a postdoc in my group, and he called it the CAL language, and it's a data flow language, and the formal specification of the video coding standards is in the form of CAL programs. And, it continues to this day to be specified that way. So it can be done. Yeah. It's not the tradition. And I think that part of the reason it's not the tradition in many fields is that it's trying to stay less biased, right? If you choose a language, a formal language to specify it in, that might be giving too much favor to the people who dominate that language, who have developed the tools to support it, for example, and so on. The other reason that I think also crops up in standardization processes is that people often want the ambiguity, right? I mean, look at UML standards, right? There's a definite resistance to nailing down the semantics, because if you nail down the semantics, then inevitably there's going to be people in the room who no longer conform with the standard, and they're not going to like that. So they like the ambiguity in the standard.
Okay, thank you. Hisham, you're next. Go ahead.
Yeah, so thank you very much, Professor Ed, for excellent presentation as usual. You mentioned a book about the structure of scientific revolutions,
Yes.
and it's a good book, but some of its stuff is not clear to me. But for example, at the beginning, he says the structure of scientific revolution start with normal science, with a paradigm and dedication to solving puzzles, followed by serious anomalies, which lead to crisis, and finally resolution of the crisis by a new paradigm. So, what is your opinion on this?
Well, I mean, so Thomas Kuhn's book was very controversial. I mean,
I agree.
Yeah, he, found himself in the middle of a swirling debate around philosophy of science for a long time. And, I think the thesis has its strengths and weaknesses, but I think overall, I think it gives very useful observations about science. I think in engineering, we're in a little bit of a different situation, though. One of the things that I love about working in computer science is that we can invent our own realities, right? So creating new paradigms happens much more often in our field than it does in science. And it happens, without a crisis and a revolution. So, new paradigms are cropping up all the time. And there's always, people resisting them. Anytime there's a new programming language, the old guard is offended and, you sort of have to wait for them to die out, like Thomas Kuhn said, before, the new paradigm takes over. But that certainly happens. But also we do see, new programming languages that actually do catch on and develop some staying power. So I think that's, gives us in a sense a much richer ecosystem of paradigms than what the scientists have. So
Fantastic. Well, on that note, we have just reached the top of the hour, and I want to have everyone join me in giving a round of applause to Edward. Thank you, Edward. You don't need to applaud yourself.
Thank you very much. This is excellent presentation. Thank you.
All right. So as my CEO at Sun Microsystems taught me, always close your meetings down on time. So thank you very much, Edward. Fabulous presentation. And we'll see you all next week. Same time, same channel. Thank you.
thank you all. Bye-bye.